Hi everyone, my name is Vikram Sri and today I'm going to present our work on learning to assess danger from movies for cooperative escape planning in hazardous environments. So let us look at this setup. It consists of search and rescue environment shown by the building over here. There is a survivor who is stuck in the building and there is a ground robot with knowledge of the map. Now there are two goals for the robot. First, develop a shared perception of danger about the surrounding and then use that danger knowledge to plan a safe path. Now, the key challenge is how can the robot leverage human sensing capabilities to assess the scene danger? Now, let us look into some related work in the area. So, first, we have seen that there is lack of models tested for high level scene understanding, such as danger perception, and also there are no large scale image data set from search and rescue environments. Now, in 2019, a disk dataset was published, which consists of simulated images of post-disaster scenarios with depth and segmentation labels as shown in the images in the right. Now, this data was from limited environments and there were no danger ratings for the images. In addition to that, there were no descriptions present for the images. Now, our key contributions are as follows. First, we developed a dataset for visuolingual danger perception from realistic hazardous images. Then we assess the performance of existing machine learning models for visual and language perception of danger. Then we proposed a Bayesian fusion model to improve danger estimate by combining the two modalities together. And finally, we tested the role of danger perception in mission success by leveraging a risk-aware path planner. Now let us start by looking into the hazardous environment dataset. So in our dataset, there are 1,000 images taken from 20 realistic sources like movies and TV series. And each one of those images have been labeled by Amazon Mechanical Turk workers by 15 of them. So there are 15 ratings and words also associated with each one of those images. And some of the images are shown on the right over here. So for example, for this particular image, you can see the danger ratings. And we find that a large number of people believe that it is of danger level 5 and the corresponding words are flood, cold, water, sinking, etc. So two observations can be made from this example. First, different people have different danger opinions that supports our probabilistic danger model. And second is that words contains details beyond what is present in the image. For example, cold over here goes beyond what is present in the image. So that comes from human experience. Now let us first look into the visual danger perception part. So the visual classifier consists of input as the robot's camera images and the output is the confidence map. So for example, C1 corresponds to danger level 1 and C5 corresponds to danger level 5 and so on. Now for model training, we are using KL divergence loss and we are using two metrics for quantifying the performance, namely the top one accuracy and the root mean squared error. Now, among the candidate models that we tested, VGGNet performs the best, and you can look into our paper for more quantitative results. Now, our language perception module consists of input as the words and the output as the danger rating or the confidence for each one of the danger values. And we are using the same metrics as before. And out of all the models that we tested, support vector machine classifier performs the best. And here are some of the words and their corresponding danger predictions that we got from our model. So for example, fire, explosion, and collapse have a danger prediction of 5, while gathering, dirty, and night has a danger prediction of 1. Now let us look into the fusion module. So first, some notations. So D denotes the danger level, and YV denotes the visual danger prediction, and YL denotes the language danger prediction. So assuming conditional independence of the two modalities that we have, we can split the task of assessing danger into two subtasks of assessing danger from each one of the modalities individually. So the first one is the vision one and the next one is the language one. So these are the likelihood functions which we need to learn from the data. And here are the likelihood functions that we learned. Now looking at some quantitative results, so we used VGGNet for visual perception and SVM for the language perception. And here are the results. And we found that combining the visual and language modalities give us the best performance. And specifically, we saw that there is 1% point improvement in top 1 accuracy and 17% improvement in the RMSE. Now let us look into the risk aware planner. So the goal is to use the danger information to safely navigate to an exit. And the assumption is that the world is divided into grid, and each node in the grid depicts certain hazards like flood, fire, etc. over here. Now, pi denotes the path from the start to the exit, and S denotes the survival probability while traversing from node Vi to Vi plus 1. So the objective function for the risk aware planner is basically the overall probability of traversing from the start to the end of the path. Now this is a stochastic optimization problem which can be converted into deterministic optimization problem by incorporating a parameter called tau, which is the danger threshold that human and robot team can sustain. Now let us look at some of the qualitative results from our simulations. So we are using the shortest path planner as our baseline, and we can see that if we start at a certain location, then the robot human team goes to the shortest path to the exit, and it encounters 5 nodes of very low survivability. And if we look into the multimodal danger sensing case, then we find that starting with the same location, it takes a much longer path. However, it encounters only one node of low survivability, which shows that it's more safer as compared to the shortest path planner. So the takeaway is that danger perception during search and rescue missions is critical, and combining visual and language modalities can improve danger perception. And finally, a risk-aware planner can take advantage of perceived danger and intelligently plan paths that avoid hazardous regions. Thank you.